let us start with insertion sort. Let us assume the following array. We will work from left to right by examining each item and compare it to the item on its left. We will then insert it in the correct position in the array. Part of our array will be sorted as we progress. It will be green in color. The first element is 2, and since there is no element to the left of 2, we will consider it as sorted. The second element is 8. To the left of 8 is 2 and 2 is less than 8, so 2 and 8 are sorted. The next element is 5, and 8 being greater than 5, we will swap their positions. Now the sorted array is 2, 5, 8 and 3, 9, 4. Now we will consider 3. Since 3 is less than 8 and 3 is less than 5, we will again swap their positions and the sorted array will be 2, 3, 5, 8 and 9, 4. The next element is 9, and since 8 is less than 9, no swapping will occur. The next element is 4, and since 4 is less than 9, 8 and 5, swapping will occur and we will get a final sorted array which is 2, 3, 4, 5, 8, 9. Let us learn bubble sort now. Let us consider the following array. We will compare executive items. If the element to the left is greater than the right element, we will swap. Since 2 is less than 8, no swapping will occur. Since 8 is greater than 5, we will switch their positions. Now, we will consider 8 and 3. Since 8 is greater than 3, we will swap their positions. Now, we will again consider 5 and 3. And since 3 is less than 5, therefore we will swap their positions. We will swap the positions until we get the minimum element to the left and maximum element to the right. Therefore, the sorted array will be 1, 2, 3, 4, 5, 8 and 9. Now let us learn quicksort. Quicksort works on recursive algorithm. In quicksort, we consider a pivot element for which 3 conditions need to be satisfied. First, pivot element is in its correct position in final sorted array, which means item to the left are smaller and item to the right are larger. Consider the following array. Choose a pivot element, let it be 3. Move this element to the extreme right of the array. Now we have to choose 2 items. Item from left being larger than the pivot element, item from right being smaller than the pivot element. In this array, starting with the procedure, 6 is item from left and 1 is item from right. Now we will swap their elements. Now 5 is item from left and 0 is item from right. Swap their positions. One more time, this time item from left has greater index than item from right, therefore no swapping occurs. Now we swap item from left with our pivot element, which is 3. Now 3 is in its correct position as it satisfies all the 3 conditions. Since quicksort is recursive, we will again choose a pivot element. Let it be 7 now. Move 7 to the end. Now item from left is 8 and item from right is 6. Since 6 is less than 8, we will swap their positions. Again, now let 8 be item from left and 5 be item from right. Bringing 7 pivot to its original position, we get lesser elements to the left and larger elements to the right. Now 3 and 7 are in its correct position. By following the concept of recursion, we will sort the rest of the array and we will get our final array, which is 0, 1, 2, 3, 5, 6, 7 and 8. Now we will learn selection sort. We will keep a track of current minimum and current item with red and blue arrow respectively. Set the current minimum and current item to the first number of the unsorted array, which is 2. Now process looking for a smaller number than this element, which in this array is 1. Set it as current minimum. Now swap 1 and 2. Now set 8 as current minimum. Scan remainder of array for smaller number updating current minimum. As we progress, at the end we find 2. Swap it with 8. Following the steps, we now swap 5 and 3. Simultaneously, we will swap 5 and 4, 9 and 5, and 9 and 8, and we will get a sorted array which is 1, 2, 3, 4, 5, 8, 9. Let us now learn merge sort. Merge sort is done recursively. It works in divide and conquer technique. Let the array be. We will find the midpoint of the array and divide the array into two halves until we get individual elements. Now to sort the array, we will follow reverse recursive way technique. To sort, examine individual items and compare their values and merge them into temporary arrays. Following reverse recursion, compare 2, 8, 5, 3, 9, 4, 1, 7 in such a way that the lesser element is to the left and the greater element is to the right. Examine individual elements and compare their values and merge them into temporary arrays. Reverse back the recursion and merge smaller arrays into larger ones, inserting items in correct order so that you get the final merged array, which is 1, 2, 3, 4, 5, 7, 8, 9.
In a search, we start from the leftmost element of the array and one by one compare x with each element of the array. If x matches with an element, we return the index. If x doesn't match with any of the elements, we return -1. Search, we begin with the middle element of the whole array as a search key. If the value of search key is equal to the item, then we return an index of the search key. If the value of search key is less than item in the middle of the interval, then we narrow the interval to the lower half, otherwise we narrow it to the upper half. We repeatedly check from the second point until the value is found or the interval is empty. Compare x with the middle element. If x matches with the middle element, we return the mid index. Else, if x is greater than the mid element, then x can only lie in the right half subarray. So we recur for the right half. Else, if x is smaller, then we recur for left half. Binary search algorithm can be implemented in the two ways. First, iteration method, and second, recursive method. The major difference between iterative and recursive version of binary search is that the recursive version has space complexity of O log n, while the iterative version has space complexity of O1. Hence, even though recursive version may be easy to implement, the iterative version is efficient.